Good morning everyone. Myself Muskan from B.Sc Chemistry Honors second year. Today I am going to make an audio recording lecture for visual impaired students on chapter Diazonium salt of organic chemistry. Introduction. RNA diazonium salts were discovered by John Peter Grayson in 1858. They have the general formula ARN2X negative, where Ar stands for the alkyl group and X may be any anion such as Cl negative, Br negative, NO3 negative, HSO4 negative, BF3 negative, etc. Aliphatic diazonium salts are also known, but they are highly unstable. They rapidly decompose even at low temperature, forming carbocation and nitrogen gas. R N positive triple bond and X negative, R positive plus N2 plus X negative. Therefore, in this unit, we shall discuss the chemistry and synthetic application of RNA diazonium salt only, particularly with reference to benzene diazonium chloride. Nomenclature. Diazonium salt are named by adding the suffix diazonium to the name of the aromatic compound followed by the name of the anion. For example, benzene diazonium chloride, para-toluene diazonium hydrogen sulfate, para-nitrogen benzene diazonium fluoborate, para-chlorobenzene diazonium bromide. Structure of benzene diazonium chloride. Number 1. Molecular formula. The molecular formula of benzene diazonium chloride as determined from analytic data and molecular weight determination is C6H5N2Cl. Number 2. Grease structure. Grease proposed structure 1 for benzene diazonium chloride in which both the nitrogen atoms were directly linked to the benzene nucleons. This structure, however, failed to account for the following facts. Number 1. Its salt-like character. Number 2. Displacement of both the nitrogen atoms by a univalent atom or group in the most of its reaction. C6H5N2Cl बनेगा C6H5X where X is equals to H, OH, OR, Cl, Br, I, Cn, etc. Number 3. Its reduction to phenylhydrazine in which only one nitrogen is attached to the benzene ring C6H5N2Cl. Catalyst SnCl2 or Na2SO3 product C6H5NH2 जो कि है फिनाइल हाइड्रोजन. Number 4. Formation of azo compound by coupling reactions C6H5N N2Cl plus C6H5Y बनेगा C6H5N double bond N C6H4Y N azo compound where Y is equals to OH or NH2. Number 5. Formation of aromatic diazonium salt from penta substituted anilines, that is 2356 tetrabromosulfenanilic acid. Catalyst NaNO2 or HCl 273 to 278 Kelvin. Product 2356 tetrabromo 4 sulfobenzene diazonium chloride. Number 3. Kekulé structure. Kekulé proposed structure 2 for benzene diazonium chloride in which only one nitrogen was linked to the benzene nucleus C6H5N double bond NCl. Evidence in favor. Structure 2. Explain most of the drawback of grease structure 1 such as its reduction to phenyl hydrazine, formation of azo compounds by coupling reactions, preparation of diazonium salt from penta substituted anilines, and displacement of both the nitrogen's atom by a univalent atom or group. Point against Kekulé structure. Structure 2 can't explain. Number 1, its salt-like structure. Number 2, its instability as compared to azo compound since both contain N double bond and linkage. Fourth point, Bloom-strand structure. Bloom-strand structure suggested structure 3 for the benzene diazonium chloride in which the nitrogen attached to the benzene ring is pentavalent while the other is trivalent C6H5 सिंगल बॉन्ड N पॉजिटिव, ट्रिपल बॉन्ड N Cl नेगेटिव। स्ट्रक्चर 3 है। Evidence in support. It explain all the objection of structure 1 and 2. Structure 3 is further supported by the following fact. Number 1, its ready solubility in water but not in common organic solvent. Its complete ionization as shown by conductivity measurement. The presence of a triple bond as shown by infrared spectroscopy. Its instability as compared to azo compounds. It explains the geometrical isomerism as shown by diazoids or diazoids, which are the metallic salts of diazonium hydroxide. C6H5 N positive triple bond NCl plus OH, benzene diazonium chloride. Catalyst NaOH HCl, product benzene diazonium hydroxide. Catalyst HCl NaOH, product benzene diazohydroxide or benzene diazotonic acid. Catalyst NaOH HCl, product sodium benzene diazoate. The benzene azotate can exist as a pair of geometrical isomerism due to hindered rotation about the N double bond N bond. Sine form or antiform. SYN sine form sodium benzene and diazotate. Antiform example sodium benzene isodiazotate. Preparation of diazonium salt. Aromatic diazonium salt are generally prepared by adding a cold aqueous solution of sodium nitrate to the solution or suspension of a primary aromatic amine in an acid at 273 to 278 Kelvin. ArNH2 primary amine plus NaNO2 plus 2HX as a reactant, 273 to 278 Kelvin. Product arene diazonium salt plus NaX plus 2H2. Diazonium salt are also formed when aromatic primary amine react with a nitrate ester such as amyl nitrite. The nitrite esters needed for the purpose are prepared by treatment of alcohol with nitrous acid. Thus, amyl alcohol plus HNO2 product amyl nitrite plus H2O. The process of conversion of primary aromatic amine into its diazonium salt is called diazotization. General procedure for diazotization. The primary aromatic amine is dissolved or suspended in a dilute acid such as HCl, H2SO4, etc. 3 moles of the acid are generally used for every mole of the amine to be diazotized. 1 mole to form the salt of the amine, 1 mole to liberate a nitrous acid from sodium nitrite, and 1 mole to keep the reaction mixture acidic enough to suppress the undesirable side reaction such as coupling of the diazonium salt thus formed with the free amine. The amine solution is cooled and such as coupling of the diazonium salt. The amine solution is cooled and a cold aqueous solution of sodium nitrate is added slowly to it at such a rate that the temperature of the reaction mixture does not rise above 278 Kelvin. The addition of sodium nitrate solution is stopped as soon as a reaction mixture does not rise above 278 Kelvin. The addition of sodium nitrate solution is stopped as soon as a reaction mixture does not rise as soon as few drops of the reaction mixture produces a blue color with starch potassium iodide paper showing the presence of unreacted nitrous acid in the reaction mixture. Too much excess of nitrous acid is generally avoided since it subsequently interferes with the reaction of diazonium salt. The excess of nitrous acid may be destroyed by the addition of urea. यूरिया प्लस 2HONO बनाएंगे प्रोडक्ट N2 plus CO2 plus 3H2. Since diazonium salt slowly decompose even at low temperature 273 to 278 Kelvin, they are used immediately after preparation. Mechanism. The diazotization of amine is believed to occur by the following mechanism. ONOH plus H, O double bond N, O positive H2. product and positive double bond O plus H2O as a diazonium cation. Evidence in support this mechanism is supported by the observation that aromatic amine containing electron withdrawing groups such as NO2 are less easy to diazotize. This is due to the reason that the nucleophilicity of the amino group is reduced due to the electron withdrawing effect of the NO2 group as shown below. Such amines can however be diazotized in acetic acid. Conversely, aromatic amines containing electron donating group at ortho and para position, example orthotoluenide, toluidine, para-anisidine, undergo diazotization much more readily than aniline. Stability of diazonium salt. Aromatic diazonium salt are much more stable than aliphatic diazonium salt due to dispersal of the positive charge over the benzene ring as shown below. Alternatively, the instability of diazonium salt is due to their tendency to eliminate an exceptionally stable molecule of nitrogen to form carbocations, etc. That is, aliphatic diazonium salt R and positive triple bond NX negative product R positive alkyl carbocation plus N triple bond N plus X negative. एरोमेटिक डाइजोनियम सोल्ट बनाता है फिनाइल कार्बोकेटाइन प्लस N ट्रिपल बॉन्ड N plus X negative. Since the phenyl or aryl carbocation is much less stable than alkyl carbocation, therefore aromatic diazonium salt have much lower tendency to eliminate nitrogen than aliphatic diazonium salt. In other words, aromatic diazonium salt are much more stable than the aliphatic diazonium salt. Physical properties. Arene diazonium salt are generally colorless crystalline solid highly soluble in water. Many diazonium salt, especially nitrides, are dangerously explosive in the dry state. Therefore, they are never isolated but are usually prepared in situ and used immediately after this preparation. However, certain diazonium salts such as fluoroborates and are relatively insoluble in water and are stable enough to be dried and stored. Some diazonium salt also form complexes with metallic salt such as zinc chloride, etc. These complexes are generally insoluble. Chemical properties. Arene diazonium salt are highly reactive compound. Their high reactivity arises due to excellent leaving ability of the diazo group as nitrogen gas N2. They are therefore extremely useful synthetic reagent in organic chemistry. The reactions of diazonium salt are broadly divided into two categories. Reaction in which the diazo group is replaced by monovalent atom or groups. B. Reaction in which the nitrogen atom are retained. A. Reaction in which the diazo group is replaced by monovalent atom or group. Some important reaction of this category along with their synthetic application are discussed given below. Number 1. Replacement by hydrogen deamination. The replacement of the diazo group by hydrogen or the reduction of diazonium salt to arenes is usually brought about by treating a diazonium salt with hypophosphorus H3PO2 acid at room temperature, preferably in presence of Cu salt as a catalyst. The reaction can also be carried out by treating amines with sodium nitrite and hypophosphorus acid as diazotizing reagent. Alternatively, diazo group may be replaced by hydrogen by heating arene diazonium salt with ethanol. For example, arene diazonium salt plus CH3CH2OH. Heat देकर arene as a product plus N2 plus HX plus CH3CHO. This whole process involving the diazotization of an amine followed by reduction of the diazonium salt or replacement of the diazo group by hydrogen is called deamination. It may be emphasized here that during the reaction of diazonium salt with ethanol, two products are usually obtained via one involving the replacement of diazo group by hydrogen as discussed above and the other by the ethoxy group. The relative amount of the two products, however, depend upon the nature and diazo compound and the ethanol used. If a minus I group is present in the nucleus and ethanol is used. The replacement of diazo group by hydrogen predominates. If on the other hand methanol is used, the predominant product is aryl methyl ether, that is anisole. Benzene diazonium chloride plus CH3OH, that is product anisole plus N2 plus HCl. Mechanism: the reaction occurs by a free radical mechanism as illustrated. Propagation. Synthetic applications. The importance of deamination is illustrated by the following applications. Number 1, synthesis of metabromotoluene. CH3 बेंजीन के ऊपर CH3NH2 पैराटोलुनाइड, CH3CO twice O pyridine acetylation, CH3NHCO CH3 पैरामिथोक्सी एसिटाइनिलीड, उसका ब्रोमिनेशन 2 ब्रोमो 4 मिथाइल एसिटाइनालाइड, एसिटाइनालाइड. कैटलिस्ट 70% H2SO for heat hydrolysis product 2 bromo 4 methyl aniline. Catalyst NaNO2 HCl diazotization product benzene diazonium salt. H3PO2 H2O Cu positive deamination metabromotoluene. Recall, metabromotoluene can't be prepared by direct bromination of toluene or Friedel-Crafts alkylation or bromination due to ortho-para-directing nature of the methyl group and the bromine atom. Number 2, synthesis of 1,3,5-tribromobenzene or sim-tribromobenzene. Aniline का bromination 2,4,6-tribromoaniline. Again diazotization 1,3,5 dibromobenzene, tribromobenzene. Number 3, synthesis of 3,5-tribromo dibromotoluene, paratoluenide to 3,5-dibromotoluene as a bromination and diazotization. Recall, direct bromination of toluene with Br2 FeBr3 gives 2,4-dibromotoluene. Number 2, replacement by hydroxyl group OH, synthesis of phenols. Diazonium salt react with water in presence of acid to form phenols. The reaction is generally carried out by adding the solution of diazonium salt to a large volume of boiling dilute sulfuric acid. The acidic condition minimizes the side reaction involving the coupling of phenol with diazonium salts. Mechanism: this reaction occurs by SN1 mechanism as shown below. Diazonium cation C6N5 and positive triple bond N. Slow process: phenyl cation C6H5 positive plus N triple bond N. Fast reaction with base C6H5 as a product C6H5O positive H2 H positive C6H5OH plus H positive phenol. Synthetic application: this reaction is especially important since only a few methods are available for the direct introduction of a hydroxyl group into benzene nucleus. Synthesis of meta-nitrophenol, meta-nitroaniline का diazotization meta-nitrophenol देगा with dilute H2SO4 or heat. Number 3, replacement by halogens. Different methods are used depending upon the halogen to be introduced. Number 1, replacement by chlorine or bromine, Sandmeyer reaction. Aryl chloride and bromide can be easily prepared by treating a freshly prepared cold aqueous solution of an arene diazotization salt with a solution of cuprous chloride in hydrochloric acid or cuprous bromide in hydrobromic acid. This reaction is called Sandmeyer reaction and gives aryl halide in 60 to 80% yield. Benzene diazonium salt with catalyst CuBr HBr Product aryl bromide plus N2 plus X negative. Benzene diazonium halide with catalyst CuCl oblique में HCl. As a product, aryl chloride gives plus N2 plus X negative. For example, benzene diazonium chloride with catalyst CuCl oblique HCl and with catalyst CuBr oblique H2 HBr. First product is chlorobenzene plus N2 plus Cl negative. Second product is C6H5Br bromobenzene plus N2 plus Cl negative. It may be noted that here that is the halogen which is attached to copper which enters the nucleus. Mechanism of Sandmeyer reaction is believed to occur by free radical pathway as determination below. CuCl plus HCl as a product, CuCl2 negative plus H positive. Gattermann reaction, it is a modification of the Sandmeyer reaction in which copper powder and a halogen and a hydrogen halide are used instead of cuprous chloride dissolved in the corresponding hydrogen halide. ArBr, Ar N positive, triple bond NX negative. Reactant as a catalyst Cu oblique HBr and Cu oblique HCl. First product is ArBr, second product is ArCl. Yields are often lower, around 40% than those obtained by Sandmeyer reaction. Synthetic application, synthetic of 1,2,3 tribromobenzene. Para-nitroaniline to 3,4,5 tribromobenzene. Product reactant para-nitroaniline catalyst bromination Br2CH3COOH. Product 2,6-dibromo 4-nitroaniline. Then azotization and Sandmeyer reaction and product is 3,4,5 tribromo nitrobenzene. Then deamination and product gives 1,2,3 tribromobenzene. B. Replacement of iodine. The replacement of diazo group by iodine does not require cuprous halide or copper as catalyst. It is simply achieved by treating a diazonium salt with potassium iodide or a solution of iodine in potassium iodide. Ar N positive triple bond N Cl negative plus Ki arrow Ar I plus N2 plus KCl aryl iodide. Synthesis of para-iodonitrobenzene. Para-nitroaniline reactant catalyst NaNO2 oblique में H2SO4 273 to 278 Kelvin diazotization reaction. Product benzene with NO2 and N2 positive HSO4 negative. Catalyst I2 oblique Ki. Product para-iodonitrobenzene. Benzene with NO2 and I. NO2 and I. Replacement by fluorine, that is Balch-Simon reaction. When an aqueous solution of diazonium salt is treated with fluoroboric acid HbF4, diazonium fluoroborate gets precipitated. It is filtered and dried. Unlike other diazonium salt, diazonium fluoroborate are fairly stable compound. When dry diazonium fluoroborate is heated, it decomposes to produce aryl fluoride and boron trifluoride. For example, Ar and positive Cl negative plus HbF4. Product diazonium fluoroborate gives Ar2 positive BF4 negative plus HCl. Mechanism. The reaction occurs by SN1 mechanism as shown below. Diazonium fluoroborate Ar and positive triple bond and BF4 negative. Slow process. Ar positive plus BF3 negative gives aryl fluoride ArF plus BF3. Synthetic application, synthesis of fluorobenzene, aniline, benzene with NH2, catalyst NaNO2 HCl 273 to 278 Kelvin gives diazonium salt, benzene with N2 positive Cl negative. Catalyst HbF4 gives product benzene diazonium fluoroborate, benzene with N2 positive plus BF4 negative. Gives heat and gives product fluorobenzene benzene with F plus BFT plus N2. Replacement by the cyano-CN group. Synthesis of nitriles. Aryl nitriles can be prepared by treating a diazonium salt with cuprous cyanide or potassium cyanide and copper powder. To avoid the loss of cyanide as HCN, the diazonium salt solution is first neutralized with sodium carbonate and then treated with cuprous chloride. AR N positive triple bond X negative. Catalyst number 1 neutralize with Na2CO3. Catalyst number 2 CuCN or KCN with Cu gives product ArCN plus N2 aryl nitrile. This reaction is called modified Sandmeyer reaction. Synthetic application. Since hydrolysis of nitriles gives carboxylic acid, therefore synthesis of nitriles provide us with an excellent method for the preparation of carboxylic acid from nitro compound. For example, toluene to para-toluene nitrile. Toluene as a reactant gives product para-nitro-toluene with nitration. Gives product para-toluenide with reduction. Gives product benzene diazonium salt with toluene diazotization reaction, then hydrolysis, and gives product para-toluic acid. Replacement number 5 replacement by the nitro group NO2. Nitro compound are generally prepared by treating an arene diazonium fluoroborate with an aqueous solution of sodium nitrite in presence of copper powder. Benzene diazonium chloride, benzene with N2Cl as a catalyst HbF4 and gives product benzene fluoroborate. Catalyst NaNO2 or Cu gives product nitrobenzene plus N2 plus NaBF4. Replacement by an arsenic acid ASO3H2 group Bart reaction. Treatment of an arene diazonium salt with sodium arsenite in presence of copper sulfate followed by acidification gives an aryl arsenic acid. For example, C6H5 N positive triple bond NCl negative benzene diazonium chloride plus Na3ASO3. Catalyst CuSO4 and product C6H5ASO3 Na2 plus NaCl plus N2 with 2HCl gives product C6H5ASO3 H2 plus 2 NaCl phenyl arsenic acid plus में salt. 7th point replacement by an aryl group Gomberg-Bachmann reaction. When an arene diazonium salt is treated with an aromatic compound liquid or its solution in an inert solvent, if solid, in presence of an aqueous alkali by aryl are formed, yield are usually less than 40%. Mechanism. This reaction is believed to occur by free radical mechanism in alkaline medium. Diazonium salt are converted one to the corresponding azo compound with decomposed to produce aryl radicals. B. Reaction in which nitrogen is retained. Number 1. Reduction to aryl hydrazenes. Arene diazonium salt upon reduction gives good yields of aryl hydrazenes. This reduction can be brought about by a number of reagents such as stannous chloride, hydrochloric acid, sodium sulfite, sodium hydrosulfite, and even electrolytically. Reactant AR N positive triple bond NX negative. Reactant with reactant SnCl2 HCl or Na2SO3 gives product ArNH2 aryl hydrazine. If however strong reducing agent such as zinc HCl is used, the product is an aromatic amine. Benzene diazonium chloride with catalyst ZnHCl gives phenyl hydrazine C6H5NH2 with Zn-HCl gives product amine aniline C6H5NH2 plus NH3. Mechanism of reduction of diazonium salt with sodium sulfide. The reaction probably occurs through nucleophilic attack by the sulfur atom of the sulfide ion on both the nitrogen atoms, forming the dianion of hydrazine sulfonic acid, which is then converted into hydrazine in presence of acid. ArN plus triple bond NCl plus SO2 gives aryl hydrazine plus 2NaSO4. Number 2, coupling reaction. Arene diazonium salt react with highly reactive electron-rich aromatic compounds such as phenols and amines to form brightly colored azo compound Ar and double bond NAr. This reaction is known as coupling reaction and is extensively used in azo dye industry, whereas coupling with phenol occur in basic medium pH 9 to 10, that of amines occur in faintly acidic medium, that is pH 4 to 5 at 273 to 278 Kelvin. Benzene diazonium chloride plus phenol with pH 9 to 10 and temperature 273 Kelvin to 278 Kelvin, it gives product para hydroxyazobenzene, that is orange color. Reactant benzene diazonium chloride with aniline and pH 4 to 5 with temperature 273 to 278 Kelvin gives product benzene diazobenzene and para amino benzene with yellow color. Give para amino azobenzene with yellow color. Coupling usually occurs at para position with respect to OH or to the NH2 group. If, however, the para position is blocked, it occurs at the ortho position. For example, benzene diazonium chloride with paracresol gives 2-phenyl azo,4-methyl phenol. If a compound contains both an amino group as well as a hydroxyl group at para position with respect to each other, then the orientation of the coupling reaction can be changed by changing the pH of the medium. For example, para aminophenol with C6H5N2Cl pH 9 to 10 or with C6H5N2Cl with pH 4 to 5. First product is 4-amino 2-phenyl azophenyl. Second product is 4-amino 3-phenyl azophenyl. The well-known indicator methyl orange, which is widely used in acid-base titration, is obtained by coupling the diazonium salt of sulfa-anilic acid with N and dimethyl aniline. Mechanism of coupling reaction. The coupling reaction between benzene diazonium chloride with benzene diazonium chloride and phenols or amines is an example of electrophilic substitution reaction in which diazonium ion act as the electrophile while phenol or amine act as nucleophile. A. Coupling with phenol. Since benzene diazonium chloride ions are not are only weak electrophile, therefore strong nucleophiles are needed for the reaction to occur. Further, since phenol is a weakly nucleophilic but phenoxide ion is strongly nucleophilic, therefore coupling reaction of phenol are usually carried out in alkaline medium. Benzene diazonium chloride with phenoxide ion gives product para hydroxyazobenzene. Role of pH. The pH of the medium plays an important role in the coupling of the phenol. As stated above, coupling of phenol is carried out in the weakly basic medium as explained below. Above, in the alkaline medium, the diazonium salt first form diazonium hydroxide, which immediately rearranges to diazohydroxide, which further react with alkali to form the corresponding salt called the diazotate All these three species in fact exist in equilibrium as shown below. Benzene diazonium chloride with OH and H positive gives diazonium hydroxide couples. Rearrange gives product diazohydroxide, does not couple, and gives product sodium diazotate, does not couple. Since a high concentration of OH negative ion, the equilibrium will shift in favor of diazohydroxide and diazotate, both of which do not couple. Therefore, for the desired coupling reaction to occur, the pH must be kept as low as possible in the alkaline medium. However, a too low pH would suppress the dissociation of phenol to phenoxide. Phenol couples slowly with OH negative plus H positive. Phenoxide ion gives couples quickly. Therefore, to carry out the coupling reaction, an optimum pH is needed. In actual practice, the optimum pH for such coupling reaction is between 9 to 10. B. Coupling with amine. Number 1. Tertiary amine. The mechanism of coupling reaction of diazonium salt with tertiary amine is similarly to that of the phenol, except that its coupling is carried out under weakly acidic conditions. C6H5 N positive triple bond NCl negative plus N and dimethylamine aniline with pH 4 to 5 and gives product C6H5 N double bond N with benzene and CH3 whole twice. Para N and dimethyl amino azobenzene. C. Reaction with primary and secondary amines. Coupling of diazonium salt with primary or secondary amine occur in a neutral or mildly alkaline medium. Here, NH2 group of the amine first attack the diazonium cation to form diazoaminobenzene. C6H5 and positive triple bond NCl negative plus benzene with NH2 and with catalyst CH3COONA gives the product diazoaminobenzene. However, when the diazoaminobenzene thus formed is heated in presence of acidic medium, it undergoes diazonium amino azo rearrangement to form para amino azobenzene by the following mechanism. Role of pH. In the presence of high concentration of H positive ion, the lone pair of electron on the N atom accept a proton. As a result, the amine exists predominantly in the protonated form as shown below. Benzene with NH2 is aniline, couple easily with H positive gives product anilinium ion. Benzene with NH3 positive, that is anilinium ion, does not couple. Due to benzene with NH3 positive is known as anilinium ion and that does not couple due to the absence of a lone pair of electron on the N atom. The amine is no longer nucleophile and hence the coupling reaction will not occur at a high concentration of H positive ions, that is low pH. Further, as explained above, too high alkalinity will also not favor coupling reaction by forming unreactive. Further, as explained above, too high alkalinity, high pH will also not favor coupling reaction by forming unreactive diazonium hydroxide or diazotate salt in significant amount. There is an optimum pH of 4 to 5 is employed for such coupling reaction. and that is optimum pH of 4 to 5 is employed for such coupling reactions. Thank you.